Hey guys, welcome once again to another edition of Chemistry at the House. Today we're talking about Brønsted-Lowry acids and bases. So, if you remember anything about acids and bases, one of the things we know is that there's many ways to define them, and kind of as we figured out more about bases and acids, we figured out more different ways to define them. So, at the start of the day here, what I want you to look at is we've got a reaction up top here between HCl and H2O. And below here we got a reaction between NH3 and H2O. What I would like you guys to do is I'd like you to tell me, what do you think's going to happen? Go ahead and take a stab at it. Okay, this is a tricky question. So here's the deal. One of the things we know about HCl, which is an acid, is that acids dissociate when they come into contact with water. So the H is going to split up with the Cl. What's going to happen there is we're going to see the formation of an H3O plus, and then the other part of the Cl that splits is just the Cl minus. So that H plus combines with H2O and forms H3O plus. What we're going to see happen with our base NH3 is that in the same way that an acid gave away its proton, what we're going to see happen with our base is that a base is going to take a proton, take an extra H. So now instead of having NH3, it's going to have NH4 and an OH left over. So remember, OHs is what makes things basic. H3O pluses is what makes things acidic. Here's something new we're going to throw at you, is the term conjugate acid and conjugate bases. A conjugate acid is, if you look at NH3 here and NH4, the conjugate acid is the NH3 with an extra proton. It is now a conjugate acid because it has an extra proton. So comparing NH3 to NH4, NH4 plus is more acidic than NH3. So we would call NH3 a base and NH4 a conjugate acid. Comparing water with OH minus, water was kind of acting like a base acting like an acid between our very basic NH3 and our more acidic H2O. Even though it's neutral, it's more acidic than a base. So this H2O was an acid, and now it is, the OH became a conjugate base. So we're going to spend a lot of today talking about conjugate acids and conjugate bases. What we're really doing is we're just comparing two solutions as products and reactants. Our reactants are going to be called acids and bases, or Brønsted-Lowry acids, Brønsted-Lowry bases. That's the new term. And then our products over here on the right side, they're going to be called either conjugate acids or conjugate bases. Let's talk more about conjugate acids and conjugate bases. So yesterday or last week, we talked about Arrhenius acids and bases, which is to say that acids form H pluses and bases form OH minuses. In the previous slide there, we showed you that acids are going to dissociate. They are going to form H pluses. Bases are going to dissociate to form OH minuses. Brønsted-Lowry, still all of the Arrhenius things are true, but it just talks a little bit more about the progress, the whole entire reaction. And it says that acids are going to donate protons. That's true. An acid is going to split up and donate its proton to water, for example. And bases are going to accept protons. That's also true. We see this all the time, that bases are going to accept H's, forming those OH minuses in that solution. So these are two true facts about Brønsted-Lowry acids and bases. It's easy to see with some examples. It's kind of harder to see with other examples. So we're going to look at some examples that best demonstrate a Brønsted-Lowry type definition of acids and bases. Okay, so here's a reaction on the bottom here. NH3 plus H2O goes to NH4 plus OH minus. This is the chemical reaction. Just above it are kind of some ball and stick models. Take a moment and kind of look over what is happening here. So take a moment, look over it, try and tell me what's happening, what's changing. Hopefully you saw here that H2O loses one of its H's, one of these gray balls, and one of these gray balls goes to NH4 plus. That's what we want you to see from there. Remember, Brønsted-Lowry acid is a proton donor and Brønsted-Lowry base is a proton acceptor. So what we're going to see here is our acid, in this case H2O, is going to donate a H plus to NH4. If H2O is our acid, because it's more acidic than NH3, that means NH3 is our base. And we notice that this NH3 here is going to accept a proton from H2O. So we do see that transfer here. Other examples are a little bit different, so let's go over a couple other ones. Oh, wait, here's some definitions. So here are some things I'd like you guys to write down. A Brønsted-Lowry base gains a proton. When it does that, after it's gained the proton, we now call the new thing a conjugate acid. So it's a Brønsted-Lowry base before it has the proton. It's a conjugate acid after it has the proton. I've abbreviated Brønsted-Lowry as BL. So we'll see here, if we start with just regular old B, that could be anything, like NH3 for example, we're going to end with HB+. So for the example, NH3 was our B, we add an H to that, we get NH4+. A Brønsted-Lowry acid loses a proton. When it loses that proton, it becomes a conjugate base. So here in this case, we'll see we have some acid, which is H and then A, and then it loses that H. So for example, we have something like HCl, which is an acid. When it loses that H, it's just Cl minus. That part is called a conjugate base, the Cl minus. So HCl is a Brønsted-Lowry acid, Cl minus is a conjugate base. So those are how we use those terms. Again, see here how conjugate is used to describe things on the product side, whereas Brønsted-Lowry acids and bases are on the reactant side. And whatever is your Brønsted-Lowry acid, it always relates to conjugate bases. Brønsted-Lowry acids do not form conjugate acids because they're losing a proton, so they can't become more acidic. In order to become more acidic, you need to gain protons. In order to become more basic, you have to lose protons. So a base has to gain protons because that's what bases do. So they could never become a conjugate base, if that makes sense. They always become a conjugate acid. Hopefully that makes sense. This is kind of tricky. Fun fact as well, since we're always gaining protons, bases are usually positive, and since acids are always losing protons, they're usually negative because a proton has that positive charge, that positive 1+ charge. Okay, here is a new equation with a new acids and bases. Here's what I want you to do is I want you to match up the two things from each side that look the most similar. Go ahead and try it out. So hopefully you connected, here below is a molecule view of this wordy formula. Hopefully you connected HCO3 1- and CO3 2-. Those are kind of the same. You'll notice one has a proton, one has a little gray dot over here, and the other one does not have a proton, does not have a gray dot. You should have also connected H2O with H3O+. Again, one has 2 H's, the other one now has 3 H's. Those are conjugate pairs. Just two things that are kind of similar, the only difference between them is an H. The next thing we're going to do is we're going to determine where the acid and base is on the left side and where the conjugate acid and the conjugate base is. In order to do that, you have to look at the pairs here. So let's look at this first pair. Let's look at HCO3 1- and CO3 2-. You'll notice that HCO3 1- has more H's. So right at the bottom, you'll notice I wrote more H's is acidic and fewer H's is basic. That's the easiest way to tell them apart. That's kind of how I remember it. I just remember, if you have more H's than your pair, you're acidic. So what this is going to mean is HCO3 1-, that's an acid. And CO3 2-, that is a conjugate base. So I wrote down here Brønsted-Lowry acid, conjugate base. Notice I outlined HCO3 1- in red. Remember, red goes with acidic, red acid, and blue goes with base. Looking at the other conjugate pair, H2O and H3O+. In this case, which one has the more protons? It's that H3O+. So we would think this is more acidic, but we don't call it an acid. We call it a conjugate acid. So H3O plus is our conjugate acid. That means that H2O is our Brønsted-Lowry base. So some trends you should notice here. Acids and bases on the left side, conjugate acids, conjugate bases on the right side. So that word conjugate is different. You'll notice that an acid will always pair up with a base. And you'll notice that acids always have more protons than bases do. And you can see that also on the bottom here with the gray dots. You'll notice that I've got more gray dots over here, fewer gray dots over there. So I've got red versus blue. So far, so good? Great. Okay, here is a little time for a learning check. What I have for you guys is I have a total of 6 different chemicals. For the first 3, I want you to write what the conjugate acid would be. For the next 3, go ahead and write what the conjugate base would be. Go ahead and try these out. Okay, so we're writing a conjugate acid here for A, 1, 2, and 3. So what this is going to mean here is that these 3 chemicals are all bases. So we're going to have to write something that is more acidic. The only way to make something more acidic is to add one H to it. So NO2 1 minus becomes HNO2. NH3 becomes NH4 plus. OH minus becomes H2O. And then for the bases over here, HBr becomes Br minus. So now we're writing conjugate bases, so they have to have fewer H's. H2S becomes HS1 minus. Remember, when we're talking about conjugate acids and bases, you only gain or lose one H at a time. So H2CO3 doesn't just become CO3 2 minus, it becomes HCO3 1 minus, because you're only losing one H at a time. That's tricky. Students sometimes don't understand that. They sometimes just think, oh, I get rid of all the H's. You only get rid of one, or you only add one. So if this was, for example, NO2 2 minus, this up at top here would be HNO2 1 minus. You would only add one H, and you would only take away one negative value. Or add one positive value, whichever way you want to think about it. So put down a nice summary down here. Add H plus to write the conjugate acid, and remove an H plus to write the conjugate base. Those are 2 kind of great summaries that'll help you with problems like this. If you want to write a conjugate acid, you have to add an H. If you want to write a conjugate base, you have to remove an H. Hopefully that helps. Moving on. Here's another problem. Here's what I want you guys to do. Go ahead and pair up this reaction. Find the 2 conjugate pairs. Then I want you to tell me what's my acid, what's my base, what's my conjugate acid, what's my conjugate base. Go ahead and pause the video. Awesome. If you need more time, pause it. Otherwise, let's get started. Great. So the first thing I'm going to do is pair them up. We notice H2SO4 and HSO4 are both the same here. The only difference is an H. Same thing with H2O and H3O+. Okay, let's determine acids and bases. Remember, acids are the stuff that have the more protons. So the first thing I'm going to look at is my H2SO4 and my HSO4 1 minus. H2SO4 here has more protons, so that is my acid. It's my Bl acid. And HSO4 1 minus is going to be conjugate base. Now we can kind of figure out what the rest is. H2O is going to have to be a base, and H3O plus is going to have to be a conjugate acid. So you'll always have one base and one acid. You'll always have one conjugate base and one conjugate acid. So that's another way. Once you find the first 2, you can very easily find the second 2. However, it's not a bad idea to double check. So let's just double check here. Does H3O plus have more protons than H2O? Yes, it does. We're good. Awesome. Here are a bunch more problems. We're just going to blow right by them. Last thing I want you guys to do is I want you to look at the following 5 pairs and tell me which of these are conjugate pairs. Some of them are not, so be careful. Okay, outlined in red are your conjugate pairs. Number 1 is a conjugate pair. Number 2 is not. To make this a conjugate pair, CO3 2 minus would have to be HCO3 1 minus. Remember, with conjugate pairs, you only add or remove one H at a time. Number 3 is not a conjugate pair. It goes from, there's a ClO4 here. That doesn't match up with just the regular Cl there. So that's why it wouldn't be a conjugate pair. Number 4 is a conjugate pair. You're adding an H. So this would be a conjugate acid. This would be a base. Last one is also a conjugate pair. NH4 would be a conjugate acid. NH3 would be a base. Okay, last thing I want you guys to do, go ahead and try out these 3 problems. We're asking for either conjugate acids or conjugate bases of certain chemicals. Try these out. Pause the video if you need more time. All right, we're trying to find a conjugate base of HCO3 1 minus. So we need to make this more basic. Only way to make this more basic is to remove H's. So A is the correct answer. CO3 2 minus has one fewer H. For the next one, to find a conjugate acid, we need to add more H's. So the answer is going to be C, H2CO3. For the last two, H2O, very similar thing here. Base needs to have fewer, so it's going to be OH minus. And the conjugate acid needs to have more, so it'd be H3O plus. All right, guys, I'm going to leave you with this. This is a cheat sheet of everything we've learned so far. So hopefully by now, you'll know that if you start with ate, ite, or ide, how to name those acids. And you will know that to go from an acid, you form a conjugate base. And what you do is you'll have a proton and you remove one proton. If you have a base going to a conjugate acid, you'll start with a chemical and then you'll add an H to it. This is a good thing to copy down if you want to become a studious bear. All right, guys. Hopefully you got a lot out of this lesson. I know I got a lot teaching it. So thank you so much. Hope you had fun watching. And don't forget to have just a great day. Take care.